Hello everyone, my name is Tomotaka Wada from Kansai University in Japan. I'd like to talk about pedestrian vehicle collision avoidance support system by using fuzzy reasoning. My presentation contents is as follows. The first one is the background, and second one is I explain the conventional method. And I explain the proposed method in this presentation. And after that, I show the performance evaluation by experiments. Finally, I conclude my presentation. At first, I'll explain the research background. There are problems in the automobile traffic society, that is, traffic congestion, traffic accidents, and environmental pollution. On these issues, we will focus on safety in special. This is a graph showing the characteristics of traffic fatal accidents in 2018 from National Police Agency report. The proportion of pedestrian is 33.5%. This percent tends to be high in other elements. So I focusing on this pedestrian. There is the following research. We have proposed the PVCAS, Pedestrian Vehicle Collision Avoidance Support System, which uses wireless communication between vehicle and pedestrian. They exchange the positions from GPS and then they avoid collision by position estimation of the several second radar, 1, 2, and 3 second radar in each. The feature of PVGAS is as follows. PVGAS has an advantage that it is possible to predict invisible danger, not only around the vehicle, but also on the other side of the wall, since it is judged by radio waves. However, this system cannot adapt to pedestrians who suddenly running out the road in traffic conditions. In addition, we cannot judge whether it is dangerous or safe accurately. Since it is difficult to accurately divide between safe and dangerous, we consider a system that incorporates human subjective senses. I explain the proposed method. The risk of danger is calculated from the GPS information of vehicles and pedestrians. As I mentioned in the previous slide, for incorporating human subjective senses, we consider fuzzy logic to be one of the effective means. We use fuzzy reasoning for the calculation of this risk. The objective is warning according to the traffic situation, and we make the driver instantly aware of the danger. This slide shows the detection process from step 1 to step 4. In step 1, the acquisition of positions of car and pedestrian from GPS. The acquired information is exchanged periodically by vehicle-to-pedestrian communications. In step 2, the decision whether the pedestrian is inside or not the activation area. This blue area is the activation area. We detect pedestrians in this blue area. The size of this area is determined by D front minimum and D front max. And this area is shaped donuts shapes. Simply, the higher the vehicle speed, the larger this area. The D front minimum and D front maximum is calculated by these equations. We refer to this document shown below. We use a fuzzy logic function with 3 input and 1 output. From GPS information, 3 data such as TTC, time to collision, acceleration of vehicle, and acceleration of pedestrian. They are calculated. After that, fuzzy operation is performed, and then we calculate the risk of danger. We show the rule table and membership functions required for fuzzy operations. This membership function is from TTC as an example. We set 18 rules and input TTC acceleration and output risk of danger, lower, higher, keeping, declaration, and acceleration. Output is low, average, and high. We set other membership functions for acceleration of vehicle and acceleration of pedestrian. Low risk and high risk warnings are given in 2 stages. Low risk warning is a warning that calls attention to others. If the risk exceeds 30%, it will warn the driver with a sound. High risk warning is a warning that prompts the driver to avoid using the brakes or steering wheel immediately. If the risk exceeds 75%, it will warn the driver with sound and image. In order to investigate the effectiveness of the proposed method, we carry out experiments of 2 mobility models, such as dangerous and safe situations. The dangerous state is walking for 10 seconds, but it is assumed that they approach each other towards the yellow place. It will be possible to be collision. The vehicle and pedestrian have GNSS receivers connected to PC, and each mobility uses a Wi-SAN module as the wireless communication media, which can be used for outdoor wide area IoT wireless networks. The communication interval is 0.5 seconds, which means that the risk is calculated every 0.5 seconds and the value is updated every 0.5 seconds. The vehicle speed is average 20 to 30 km per hour. The number of trials is 21 times in each state. This slide shows a figure in the dangerous state. This figure shows an example of a warning timing in a dangerous situation. The horizontal axis represents elapsed time from the start. The left vertical axis represents the distance, and the right vertical axis represents the risk of collision. The blue line is relative distance between the vehicle and the pedestrian. The green line shows stopping distance of the vehicle, and the red line shows the degree of danger. Since there is a pedestrian in the activation area of the vehicle at 4.5 seconds, the risk is calculated. We set the threshold of 30% and 75% risk of low and high risk warnings, respectively. At 5.0 seconds, the risk is 30% and 75% risk of low and high risk warning. So low risk warning is given. At 6.0 seconds, the risk is 75% or higher, so a high risk warning is given. From these results, a high risk warning is given when there is a risk of collision. In addition, since the relative distance is 32 meters and the stopping distance is 8 meters at 6 seconds, the relative distance is longer than the stopping distance, so no collision occurs. Furthermore, a low risk warning is given 0.8 seconds before a high risk warning. Therefore, the proposed method can give warnings at an appropriate timing in the conditions. On the other hand, here is a safe state environment. Here is an example of an accurate warning in a safe state. The display of the figure, axis and legend is the same as in the previous figure. From this figure, you can see that we are giving low risk warning in this period instead of high risk warning. The overall results are shown in this table. This is the recall rate, and this is the adaptable rate. The correct decision rate indicates the performance of the entire system. The frames with this cross mark are false warnings, and this mark is true warnings. False warnings were detected twice in each. However, it turned out that the correct decision rate is more than 90%. So, in order to improve the warning error, we have to study the following 2 points. The first one, we have to reduce the communication interruption and error in a road environment by increasing RSSI. RSSI from the Y-SUN module is fluctuated according to time. So we need the stable environment. And second one is we adjust the parameters that incorporates deep learning and so on in a simulation environment. Finally, I conclude my presentation. We focus on the high proportion of pedestrians in the traffic fatal accidents. We clarify the problems of the pedestrian vehicle collision avoidance support system, PVCAS. In order to solve the problems, we have proposed a risk calculation algorithm using fuzzy logic. We have found the following results by experiments. The first one is the visualization of risk level is possible by detecting pedestrians quickly. In the second one is a multi-step high, middle, low step warnings is possible at an appropriate timing. In the future works, we have to improve the wireless communication quality to increase the RSSI in a road environment. And we have to adjust the parameters that incorporates deep learnings and so on. This is the end of my presentation. Thank you for your attention.